Okay, let's take a deep dive at type 1 non-repeating linear factors and let's try to understand what are exactly this, what are the key characteristics of this, how do we identify them, and let's take all the exam problems that we have seen for type 1 non-repeating linear factors and let's try to solve them one by one. But before solving, let's understand the basics of how should you think about non-repeating linear factors type 1 and how should you wrap your head around that one in the exam to see, okay, this is what exactly we need to do. And again, as a quick reminder, since this is going to be a crash course relevant for the last minute study, I'll be keeping the pace pretty brisk and keeping it very light and condensed in case you're interested in knowing the nitty gritties and knowing what's under the hood and what to know the details. I've put another videos in the intuition part where I'm discussing the same thing at length, and it will tell you from all the angles why we do certain things, why not certain things, and stuff like that. So the interest of time, let's get started. So if you see this equation about adding and subtracting rational expressions, we have seen this in one of the episodes in this crash course where we are talking about how to what are partial fractions all about, what are they. I think it was episode 3 or 4. Check that out if you're not checked out. So I'm just copying that as a for the sake of continuation. And what do we see here? Typically we have this partial fractions over here, okay, individual terms, and then we try to cross multiply and bring this into a rational function, rational expression here. And we know that partial fraction is nothing but doing the exact opposite of that, where you're given a rational expression like this, and our objective is to break it down back to the individual parts, the individual components of this. And these parts are nothing but partial fractions. These are fractional in nature, and these are partial because this doesn't make up the whole thing. So these are the individual blocks. And one thing that you will notice is even the given, since we're talking about type 1 non-repeating linear factors, and the two proper fractions where the degree of numerator is less than the degree of the denominator, you will see that the same pattern applies over here also, and we will see that in a couple of minutes when we do the observation. So partial fraction is nothing but taking a rational expression and decomposing that or dividing that into simpler parts which are fractional in nature, and these simple fractions are called as partial fractions. Okay, so when we combine them, you get back the rational expressions. When you uncombine them, you get the individual partial fractions. So you start with the rational expression and you end with a partial fraction. Pretty much this is what it is over here. You start with a rational expression, the same problem, okay, and you end with a partial fraction. This is a partial fraction, and our objective is whenever we try to solve the problem, we will not know what are the values of these constants. So the whole issue of partial fraction is, although we know the construct of these equations in terms of the individual fractional parts of the partial fractions, our objective is to find the value of a and b, which is nothing but over here and over here. So the whole objective of partial fraction is to express each type, based on each type, express them in some of this format, which we will see, which will have some construct of having a constant in the numerator and finding the value of those constants and putting it back in the equation. That's what we will do in all the types, and that's what I've highlighted in the red. Objective is to find this constants in the numerator a, b to get the final partial fractions, and that's all partial fractions are all about. Okay, so that was a quick recap. Now let's see, when we solve this, I'm going to just erase this. Now let's focus on just this example. Let's assume that for now, let's assume that we have already solved this problem. The actual solving we'll do in the next episode, but let's assume that we already solved this problem, okay, over here. Let me just copy that. We might be pasting it time and again. Okay, let's say I'm going to copy it. I'm going to create some room here. Okay, I'm just copy and paste it again here. Okay, all right. Now let's focus on from this point so that our focus is very clear. So let's say we have this and we know our objective is to find a and b. Okay, but we know that we have a general sense of direction of where this is heading. Okay, now let's understand some of the key observations. What's happening in this equation? In the context of partial fractions, which are proper in nature, proper fractions, and we're talking about specifically type 1 non-repeating linear factors. Okay, so let's see what's happening. Okay, I'm going to read it out and then we can apply that on the equation. Okay, this is the equation we are talking about. Okay, the denominator is in factorized form. If you see the denominator, it's already factorized. Okay, in the this is the rational expression. and this is the partial fraction. There is a partial fraction, there is a partial fraction with a and b, okay, a and b, okay. The denominator is already in the factorized format. That means it's already simplified in terms of having both are linear here also, okay. And if it's not simplified, let's say if it was quadratic, like how we saw in the last episode, if it was quadratic, then you kind of try to simplify that. For example, if these brackets were opened and you multiply that, this will become quadratic. And if it is quadratic, the first check that you need to do is, can the denominator be factorized into simple factors? That's the first check, okay. But in this case, it's already factorized, so this first step does not apply, but you'll always keep that in mind. And we have seen that when we are doing the exam questions in the last episode, okay. The other observation is, if you see here, all the factors in the denominator, okay, whether it's on the left hand side, on the rational expression side, or on the partial fraction side, all the factors are linear. That means the degree or the power of x is 1 over here and over here and over here and over here, okay. That's 1, okay. So we see that also. And then the factors, these are called as the individual factors. X plus 2 is one factor, this is factor 1, x minus 1 is factor 2. These two factors are non-repeating. It appears only once. X plus 2 appears once and x minus 1 also appears once, okay. That is after the factorization. And hence we know that these are type 1 linear factors and non-repeating. Linear meaning the degree is 1 and non-repeating means it appears just once. And that's how we kind of understand after the factorizations, and once we simplify it, we can categorize based on this particular thing, linear or it has a higher degree, or repeating or non-repeating. We can categorize this into type 1. That's another thing, okay. Now the few important things. So I want you to pay complete attention, and I'm going to go a bit slow so that you can consume what I'm trying to say. Okay, if you see here, denominator is same on both the sides, but each denominator factor is separate term in the partial fraction. What does it mean? If you take the rational expression on the left hand side, you see this is the denominator. This is a combined denominator. They are multiplied by, there are two factors are multiplied by each other. And if you see the right side, once we break them into the different parts of the partial fraction like this, then also if you see the number of terms and the denominator exactly the same, you are not going to see any new terms, okay. It's going to be exactly the same. And the only difference is, when we do the partial fractions, by virtue of it, it's going to be sum of 2 or 3 parts because of the plus sign. Each of the denominator is separated. So if you have two denominators or two factors, one denominator with two factors, each factor is separated out here individually. X plus 2 is separate, x plus 1, x minus 1 is separate, and like that. And that's how you do it. And for each factor, then you have a constant, whether 3 or 5 or a and b. That's what it's mentioned here. So the denominator is same on the both sides. The only thing is, in the way you express the parts of the partial fraction, you separate out each of the factor from this rational expression and put them as an individual term. So this whole thing becomes a term 1. This whole thing becomes a term 2. So the factors get separated out into individual terms when you move them into the partial fractions. That's another kind of guiding principle that you need to remember. And that's pretty much going to be true for all the types, because that's how you do it, because eventually you'll see that this denominator gets cancelled, and that's the reason you need to do that kind of a thing, okay. Okay, that's one. Okay, now the next three things, let me see if I can explain it better. Okay, now what do we see here? Okay, so we also see here, okay, all the terms, this is a proper fraction that we know, okay, this is a proper fraction. Why? Because the numerator and the denominator, let's see the degree of that. The degree of the numerator is 1, and the degree of the denominator here is 1, and here is 1. And if you multiply that, this will become quadratic in terms of x square, and its degree will become 2. So 1 is less than 2, and hence it's a proper fraction. And the same thing will be maintained over here also in the individual terms. If you see here individually, okay, and if you take the numerator and denominator of that, the numerator of this is, we can talk about this as 3x to the power 0, and over also we can talk about power 0 here, and here is 1 and here is 1. So the numerator degree is 0 and the denominator degree is 1, right, in both the terms for this and this, okay. That means 0 is less than 1, and both these terms individually are also proper fractions, okay, proper fractions. Let me write it down, okay. And that's what you will see. So we have to maintain this we have to maintain this, because if you don't maintain this degree, this will become an improper fraction, and that's a type 4. We're talking about type 1. So we have to always maintain the incoming rational expression was a proper fraction, and hence once you split them into the partial fraction, also the individual terms by itself are also proper fraction, where the degree is still less than the degree of the numerator is still less than the degree of the denominator. Okay, so that's kind of one thing you need to think about. And the way you think about that, let me explain that in a minute. So let me check this term. All the terms on the both sides are proper fractions. Okay, we have checked that. Okay, and since we know it's proper fraction, the way we can think about that is, okay, so we know that we have to split in this format, and we have to find the values of a and b. But if you see here, once you split it, we know that the denominator is going to be of degree 1, because it's a linear factors from here. Okay, and let's say we do not know the a and the b part. Let's say you do not know this part. Okay, let's say you do not know what to put in the constant, whether it should be just a constant or it should have some variable in x. Since we know each of this term has to be a proper fraction, meaning the degree has to be less than this, since the degree of the denominator is already 1, the nearest term that comes less than 1 is 0, something to the power of 0. Okay, because we cannot have more than 1, because if you have the same degree also, it's going to be, the term is going to become an improper fraction. Okay, and anything raised to the 0 is equal to 1. That means we're just going to have a constant, and hence we just take a and b, because this is as good as saying a multiplied by x to the power 0 and b multiplied by x to the power 0, because anything multiplied by 0 is going to be 1. And that's the reason you can think about these numerators also as a polynomial, but which just has a constant term of the polynomial with the degree is equal to 0. You can think about it that way also. And always thinking about this whole thing as a ratio of polynomials will help you, because that way you will determine that why in type 2 and type 3, what kind of x we need to take. So let me repeat it again. We have to always, if we have to maintain these terms to be proper partial fractions, the degree of the variable x should be always less than the degree of the x in the denominator, and in this case the degree is 1. So the max we can go here is with degree is equal to 0, because anything above that will make this term improper, and we don't want that. Okay, so that's another highlight of that. So, and that will be useful once I start doing type 2 and type 3 specifically. Okay, so let's check that also in this episode. Okay, we have seen that degree of the polynomial starts with 1 degree less. Okay, we have seen that, and we also covered this, and why we have to just keep it as a constant. In the case of type 1, the type 2 it will vary, because we have to maintain this term to be a proper partial fraction, and hence we can just keep it constant. We cannot put any more variables of x there, and that's the reason we have to keep it constant, otherwise it will become an improper fraction. We have covered this also. And like I said, have the notion of thinking the whole partial fraction, right, as a ratio of polynomials in the descending order. For example, if you see here, x is to the power 1, and the next we have x to the power 1. Let me erase it. Okay, so if you see here on the left hand side, we have x to the power 1, which is this, and plus we have something which is x to the power 0 with some coefficients. So the powers are decreasing, right? So you always think from that standpoint, right? For the a and b also, if you think from that standpoint, then you'll always maintain that, okay, whatever is the degree at the bottom, it's x to the power 1 plus 2x is like 2 to the x to the power 0 over here. So again the degree is decreasing, and over here it will start with 1 less degree, and there's nothing to go further because we have already hit the constant. So think about it not only as a polynomial like I have explained here, okay, but think about it of a polynomial, the partial fraction as a polynomial in the numerator, which is arranged in the descending order by the powers of x. So that way you can visualize whether the constant should have an x factor or not. And like I said, this will be more applicable when we do the rest of the videos, okay, or rest of the types, type 2 and type 3. So these are some of the observations of type 1 linear factors non-repeating in the case of partial proper fractions or proper partial fractions, okay. And this is how we need to identify, or this is how we should think about it, okay. These are like the key points. From an exam standpoint of view, once you get a problem and once you identify that, okay, it's a partial fraction and it belongs to type 1 linear factors, non-repeating. Based on this, the only thing that you need to remember to solve, there are only 3 steps. All these things you don't have to remember. Once you understand it, you can just memorize it, or it gets into your head. You don't have to actually remember any of these things. It's just more of opening up your understanding level in terms of what it is, at least at a bare minimum, even if you don't want to understand what's going on. And like I said, if you're really interested in what's happening here, check out my another video into the intuition section where I've explained this in detail, why we should think about this. And I've taken a different approach to explain this problem in detail. But if you are just focusing on exam, just this is good enough. So what did we observe? How should we solve once we identify that a problem is type 1 linear factors? Okay, there are only 3 simple steps. Factorize all the denominators and make sure it's linear. Okay, I think I did a mistake, typo mistake. Okay, factorize to ensure all the denominators are linear. That means the degree of the x variable should be 1, and they are non-repeating because it's a non-repeating linear factor type 1. So just make sure that is done. After you're done with that, just simply separate out the constants, separate out the terms using constant ABC, one constant per term. So see how many terms are there in the denominator, how many factors are in the denominator. So these are factors because they are combined. And for each factor, build each one term. Like for example, this one factor, I've got one term here and the same denominator I'm copying. This is kind of factor 2 and I have another term here, I'm copying it there. So separate it out. If there are more factors, you can keep on expanding from a plus b plus c and so forth. So separate out, keep the denominator same, see how many factors are there, and for each factor take a constant divided by just one of the factors, that will become a term here. So in this world we talk them as a factors. When separate it out by a plus or minus sign, we call them as a terms. So one factor, one term, and you can just manage the denominator so that you can count that all the denominator is covered. Okay, that's the second step for solving the problem. And the whole objective of partial fraction is just to find whatever constants you put, whether it's a, b, c, whatever constants, find the values of the constants, which we will see in the next episode how to find that, because these are the 2 important steps. Finding the value is the easiest piece. If you get this and this right, this second piece is the most important for all types of partial fractions. If you get this, your job is 95% done. Okay, and hence I'm trying to just put more minutes on this one. So once you're done with that, the simple objective is to make some mathematical manipulation, find the values of a and b and put it back in this format over here. So let's say you get the value of a and b, then you write it back in this format. A is equal to 3 and b is equal to 5, and once you write back in this format after assuming a and b, this should be a final answer. That's how you solve type 1 linear factors. Just 3 steps, okay, to understand, and then you solve the examples. In the next episodes, we will start taking those exam problems for type 1 and apply whatever we have learned here. And maybe I'll again cross-reference some of the things, and then you can understand very clearly how to find the values of A and B, and in generic how to solve this kind of problems. I'll see you in the next episodes.